Okay, so I tasked you in the last video to think a little bit about chromium. And so there's two different configurations that we're going to evaluate for chromium. So the one that we might draw or think of first on the periodic table, or when we look at the periodic table, is that chromium in its condensed configuration has a configuration of argon, and then 4s2, 3d4. But we know that from photoelectron spectroscopy and other data, right, that chromium actually has the configuration of 4s1, 3d5. And the question is why, right? What's happening here? And so we can draw out our two different configurations here using kind of the same pictures that we've used in the past. So we have our 4s state, we have our 3d state, and then we can fill in our electrons, right? So this one on the left has my paired up electrons in the 4s orbital, right? And then I have my 4 electrons in the 3d orbital. This right-hand configuration has all my electrons in the 3d orbital, or 5 electrons in 3d orbitals and 1 in the 4s. So right now I'm just going to kind of divide this slide in half, or this image in half, so we can talk about these two distinct spin states. So I'm going to give these two different names. So the one on the left, I'm going to call this our low spin state because it has a lower electron spin than the state on the right. I'm going to call this my high spin state, right? Or HS, right? And low spin is going to be LS. So these are just going to be some tags that we can use to refer to these two different states. These are going to be very common throughout inorganic chemistry. This idea of a difference between a low spin and a high spin state it's going to be something we use all the time. So what we're going to do is we're going to use the same tools that we practice with carbon to try to describe the energy of these spin states, right? And so by describing the energy of these spin states, hopefully we can compare them. Now, we might not be able to predict right out of the gate which one of these would be lower in energy, the high spin or the low spin state. But once we are given data, we want to be able to rationalize, right? We want to be able to rationalize that conclusion, right? That one of these would be higher in energy and one would be lower in energy. So let's start by just describing the energy of our electrons in these orbitals, right? And it's going to be actually different this time for our two different spin states. So on the left-hand side, we have two electrons, right, that are in 4s orbitals. And we have 4 electrons that are in 3d orbitals. So this is just describing the energy of putting these electrons into these given orbitals. On the right-hand side, right, I have 1 electron, and this E stands for energy, not electron, in the 4s orbital. And I have 5 electrons that are in 3d orbitals, right? And so this just describes the energy of putting those electrons in these orbitals. When I look at the left-hand side, my low spin state, I can see that I also have 1 Coulombic repulsion, right? And I'm going to put just a 4s here so we remember where it is. It's not necessarily true that all Coulombic repulsions would be equal, so it might be helpful to kind of designate what they are and what orbital they come from. If I look at my high spin state, I actually have no Coulombic repulsions, right? I can see that I don't have electrons paired up in any of my orbitals, right? So now I need to figure out how much of that quantum exchange energy do I have on each side, right? How many different ways could I split these electrons that would be indistinguishable? And so I have this like weird little system that I use that describes these kind of switches that we can have and kind of count them up. And so I can say that if these two switch places, right, or I could switch the first with the second spot, and that would be that 1K. I could switch the first and the third spot, and this would be another K. The first and the fourth, and this would be another value of K. right? And so these are three different exchanges that I can get just from that first electron. The second electron could switch with a third space and have another quantum exchange. With the fourth space, have another quantum exchange. And the third and fourth could switch, and I could have this last quantum exchange. This is the way that I think about and count up the total number of these quantum exchanges that are possible, right? It's just these little bounces that allow us to calculate this out. And so I see here that I have 6, right, of these quantum exchanges that are possible for my 3D electrons, right? So I can just count up essentially the bounces that I had here. This should represent all of the possible configurations that I can have that swap the places of these electrons. So let's go through the same process for my high spin system, right? So I can swap an extra time, right, for my first electron. I can swap an extra time for my second electron, an extra time for my third electron, and now my fourth electron actually also has a swap, right, with that 5th position, right? So if I'm to count up these Ks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for my high spin system, I actually have 10 of these quantum exchanges that I can possibly do in my 3D orbitals. And so this is just a way that we can create an expression, right? Again, deriving an expression, our learning objective number 3 over here, for each of these given spin states, right? So for the first step was proposing our high spin and low spin configurations for an electronic system. And our second step was deriving these expressions. So what can we do with these expressions, right? So now I have this total energy value for my high spin and my low spin state. So we know that the high spin state is actually lower in energy based on given data, right? I told you that this is something that we can get from photoelectron spectroscopy. I'm not expecting you to predict that the high spin state would be the ground state here, or the lower in energy. But now that we are given this, right, we can start to rationalize and determine, well, what on earth is happening here, right? What on earth is happening here? So let's make a new slide here. And what we want to try to describe is what is happening when it comes to chromium, right? And what's happening is that we know that the energy of our high spin state is lower than the energy of our low spin state, right? And this is, again, just based on given data. This isn't something you would necessarily predict. And so if we're going to fill this in with our energies, right, we can see that if we're going to use those same expressions we developed on the previous slide here, we know that our high spin state had the energy of a 4s electron. It had the energy for 5 electrons in 3D orbitals, and it had 10 of these quantum exchanges for my 3D orbitals. And so we can say that this is less than the energy of my low spin state, which was 2 energies for the 4s, 4 energies for the 3D, 6 of my quantum exchanges in the 3D orbitals, and that Coulombic repulsion exchange, or that Coulombic repulsion between electrons in my 4s orbital. So this is now an inequality, right? I have 2 different sides, and I'm saying that one is less than the other. So I'm going to do a little bit of rearranging here. And so what I'm going to do is I'm going to put my energy for my orbital energies on the left, and I'm going to put everything else on the right. And what this expression simplifies down to is the energy of my 3D orbital minus the energy of my 4s orbital. Right? This is just comes from moving the energy terms over to the left, is less than the Coulombic repulsion of the 4s orbital minus 4 of these quantum exchange for 3D. All right. This is an expression now, right, that's describing the true statement for why we have the high spin system as our lower in energy state. And so what we can do is we can say that this left-hand term describes the difference in energy of my orbitals, right? This just describes the difference in energy between my 3d and 4s orbitals. And on the right-hand side, what we're going to call this describes the pairing energy, right, for our system, right? This is the amount of energy that comes from needing to pair up that electron in our low spin state, right? This is what's required to get that electron paired up in that 4s orbital. And so what we can say is that for our system, which is chromium, in this case, right, the delta E is smaller than the pairing energy, right? If we're going to try to translate this to English, because right now I'm not really speaking English, right? I'm speaking chemistry. If I'm to translate this to English, what I'm trying to say is that the energy gap between the 4s and 3d orbitals is smaller than the energy that would be required to pair up the electrons. So, why does this matter so much for inorganic chemistry? Well, what ends up happening is as you move down the periodic table, our orbitals actually all get a lot closer in energy, right? If we go back and we look at some of the diagrams that we drew for these, we have that, our 1s orbital is really low in energy, and then we have our 2s, and then we have 2p, and then we have 3s, and we have 3p, and then we have 4s, and then we have the 3ds, and then we have the 4ps, right? And this diagram is getting very kind of claustrophobic here. But the idea is when we're looking at transition metals, which is what we're going to be looking at for a lot of inorganic chemistry, right? This is the region where we're working with transition metals, right? And these are the early transition metals here. And so we can see that our energies, right? Energies or energy between orbitals is getting really small. And so this is why we need to evaluate Hund's rule a little bit more for inorganic chemistry, because now that our energies between orbitals are getting small, right? And that's this delta E term, the orbital differences between our orbital energies. We're going to have a lot more cases where we have to consider a high spin and a low spin system and what the cost of that difference would be. All right. So this is the kind of problems that we're going to be digging into. And at a theoretical level, we might not be doing this for individual atoms like chromium very often. But at a theoretical level, we want to think about how the difference between orbital energies and this idea of a Coulombic repulsion and this quantum exchange energy, how all of those things interact, right, to give us a ground state and a excited state, right, or a lower energy state and a higher energy state. We're going to do some more practice with this in class, all right? So come prepared to discuss this a little bit more. There's another video that's on coordination chemistry. As we're building up these complexes, how do we study them? And that's going to be the last video before our class on before our next class. So make sure that you watch the next video as well. It's the next link on the Canvas page.